So you've been taught basically that if you take the square root of a number, like the square root of 4 is equal to 2 because 2 times 2 is equal to 4. And so this is because if I rewrote 4 as 2 squared, basically that square root undoes a square and you're left with whatever the number is underneath. So this 2 is corresponding to that 2, basically. The square root is undoing that square. So where this comes from is actually the square root symbol is special because it is a special type of exponent. So the square root is actually symbolizing a 1/2 exponent. So when we saw exponents last week, we were looking at whole number exponents and we were looking at some negative exponents. When you have fraction exponents, that's where you get radicals. And so the square root is defined as a 1/2 exponent. And how this works is 4 is equal to 2 squared. So I can rewrite that 4 as 2 squared. And then I can use my power rule of exponents, where if you have a power of a power, or 2 exponents basically one after another, you multiply those together. So 2 times 1/2 is equal to 1. So this is just 2 to the first power. And that's why the square root of 4 is equal to 2. It's because it undoes that exponent of 2, and that's because it's defined as the 1/2 power. So if radicals are sort of confusing to you, and if exponents sort of make sense to you, you can always rewrite it as an exponent, because then you just follow the rules of exponents and get the same answer. We just generally don't write it as exponents because one, it's got fractions and people tend to be afraid of fractions. 2, it's harder when you're typing stuff up to have like a fraction of a fraction. It's easier to actually, the square root symbol like on a computer is much easier to do than an exponent on top of an exponent with fractions and all that kind of stuff. So they've just come up with this symbol instead of writing the 1/2 power. So then if you say, okay, if the 1/2 is a square root, well, what is a 1/3 power? So let's say I had like 8 to the 1/3. So this is defined as what's called the cubed root, where you still have what's called the radical symbol, but we put a 3 up there to indicate that the denominator on that fraction, if you put it in exponent form, is no longer 2, but now it's 3. So whatever the denominator is, that tells you what the bottom of your, what is going on the radical. And so you want to rewrite the number inside as some exponent of 3 so that you can simplify it. So 8 is actually equal to 2 cubed. So a cubed root cancels out a cube, and it gives you the answer of 2 in this case. And if you look at it, and if you think about it in terms of that fraction form, 8 is 2 cubed, and you take it to the 1/3 power, well, 3 times 1/3 is equal to 1. Those cancel out, and you're just left with 2 to the first power. So we are just using this other symbol to indicate fractional exponents, and usually we just work with 1/3 or 1/2 of those fraction exponents. Sometimes you can have 1/4, 1/5, but that's what we're looking at here, and that's how radicals work. Is you're just dealing with a different type of exponent. We just have a different symbol for it. So when we're simplifying radicals, and this is the problem, is I try to make up numbers and it's probably going to be prime, because most of the time when I make up a number, it's prime. 264 won't be prime because I know I can divide that by 2. So let's take something like the square root of 264. So there's a square root button on your calculator. If you took that square root, you get a decimal. Most square roots, most radicals give you a decimal when you do it on your calculator. And so in math, it's harder to work with decimals. We have to round, then our answers aren't exactly accurate anymore. So we want to simplify it. And simplify in this case means that the number that's on the inside, we try to get that as small as possible. We want to try to get everything as much inside out of it. So we want to rewrite 264, and we want to write it as things that have exponents we can divide by 2, because the square root has a 1/2 exponent. And so we're essentially dividing the exponent by 2. 2 to the 1/2, 2 divided by 2 is 1. So we want to rewrite the number and group it in such a way that things have even exponents for a square root. So we do this by first doing a prime factorization. So I'm going to make a factor tree. So I have 264, and I want to split it up as two things that multiply to that number. All I know is that 2 definitely goes into 264 because 4 is an even number. So I'm going to divide 264 by 2. So that gives me 132. So 2 is prime, so I'm going to circle it. And now I want to keep going. So 132, I know 2 goes into that. So I'm going to divide that by 2, and that gives me 66. And 66, I know, is 6 times 11. So 11 is a prime number, but 6 isn't. That can still get split up. And that is 2 times 3. So you do this prime factorization, and for the square root, we want to group things in pairs whenever possible so that you can take the square root, basically, so that you can use that fact that it's the 1/2 power to simplify it. So I have 3 2's, but I want to group 2 of them together as 2 squared and then leave the third one by itself, because otherwise if I put the 3 of them together, they're not going to be a pair anymore. So if the first thing you did was just to write the prime factorization, we would have 3 2's, so that's 2 cubed, times 3 times 11. But if we look at that with your exponent being a 1/2 power, I can't simplify any of those exponents because I would still have fractions. So we want to take that 2 cubed and instead write as 2 squared times 2. There's still 3 2's there. I just rewrote it. And I'm doing this specifically because the square root divides by 2, so I need numbers I can divide by 2 for my exponents. So we have this rule with radicals where you can separate these out. If you have a whole bunch of things multiplied inside, you can separate them out so they're multiplied on the outside as like square roots. And I only want to multiply out the things that have exponents of 2. Everything else that doesn't have an exponent of 2 gets stuck together in another square root symbol. So I have the square root of 2 squared, and then times the square root of 2 times 3 times 11. So this makes sense if you think about that square root of 2 squared. If you rewrite that as its 1/2 power, that is 2 squared, and then it's to the 1/2. So 2 times 1/2 is 1, so that just cancels out and you're left with a 2. But nothing with the 2 times the 3 times 11 cancels because that's a 1/2 power. All of those exponents are 1. 1 times 1/2 is still 1/2, so it doesn't do anything. It's still inside a square root. And so we just multiply that together, 2 times 3 times 11, which is 66. So our goal is to get what's inside the square root symbol smaller. So I went from 264 to 66, and then try to get as much outside of the square root as possible. And so in this case, I was able to pull out the square root of 4, basically 2, and then I have what's left over. So I'm going to try to find some numbers that I'm not making up, because it's really difficult to make up numbers that are not prime. So let me see. There are really no good examples here. Let's see. Here, we'll just do the square root of, we want to do square root of 28, maybe. Or let's just do 280, because we'll just make it bigger, then you can kind of look at it more. So say the square root of 280. So I'm going to take 280 and I'm going to do the prime factorization. So I know that's 28 times 10. 28 is 4 times 7, so 7's prime, so I'm going to circle it. And then 4 is 2 times 2. Then 10 is 2 times 5. So we want to split this up so that we have things in pairs, because it's a square root. So I'm going to take 2 of those 2's and I'm going to combine them as a 2 squared. But everything else is going to be separate here, because I don't have anything else to pair things up with. So I'm going to rewrite this as 2 squared for my highlighted 2's. Then I have another 2, I have a 5, and then I have a 7. So we split up what has something squared, and then we keep everything else that's not squared together. The square root cancels out exponents of 2. So I'm just left with that 2. And then inside we have 2 times 5 times 7. And that comes out to 70. Now we can do the same thing, but with a cubed root. So cubed root, it's not an exponent of 3. It's like a symbol right above that little v thing, a cubed root. So when you have a cubed root, that is a 1/3 power. So you want your exponents to be grouped in 3's, because you want to be able to divide the exponent by 3 when you multiply by 1/3. So if we're doing the same number with 1/3, I'm going to group all 3 of the 2's together instead of doing 2 of them and then 1 separately, because I want to group them in 3's because it's a cubed root. So instead of 2 squared times 2, I would use the whole 2 cubed times 5 times 7. Because now my goal is to get them divided by 3, because of the 3, the cubed root. Our rules still apply, where I'm going to separate out anything that has that exponent of 3 from the things that don't. So I put the 2 cubed by itself, and then the 5 times 7. So 2 cubed cancels out the exponent of 3, because you're basically taking the exponent of 3, multiplying it by 1/3. Those cancel out. So I'm left with 2. And then I have my cubed root of 35, because 5 times 7 is 35. So we get different answers depending on whether it's a square root or a cubed root, because we have to group things differently. You group it in pairs if it's a square root, in groups of 3 if it's a cubed root. So if it's something like a 4th root, you're going to be grouping them with exponents of 4. A 5th root is grouped with exponents of 5. that's how you work with these with numbers, with radicals. And actually, when you work with variables in these, it's actually almost easier working with variables. So let's say I have a square root of w to the fifth. So this w to the fifth means that I have 5 w's multiplied together. So if we're trying to group things in pairs, instead of 5 of them, I can say, okay, I've got 2 of them, another 2, and then 1 left over. So I still have 5 w's there. I've just grouped them differently. I grouped them by 2's because it's a square root. Oops. So I just, it's the same rules as before. I didn't have to do any prime factorization here. I'm going to put everything that has the exponent of 2 together, and then everything without the exponent of 2 is separate. So again, the square root is a 1/2 power. And our rule is when you have something with exponents inside and an exponent outside, you multiply, you distribute it. So each w squared, that 2 is going to be multiplied by 1/2, leaving a w. So that square root of w squared times w squared leaves me a w times w. And then I have my square root of w. And then w times w is w squared. And you're left with square root of w. So you can group things in pairs, and with variables, it's literally just pulling things apart. You don't have to do a prime factorization. With the w times w there that I have to the 1/2, I could have instead grouped it in things that I can divide by 2. So instead of doing 2w squareds multiplied together, I could have done a w to the 4th times w. If you follow the rules of exponents here, 4 times 1/2 is 2, and so you're left with w squared. So what this means is that the square root of w to the 4th is w squared. So the square root is literally dividing exponents by 2. So anything that is squared, you can group it so that it has an even exponent, and then you're just literally dividing that exponent by 2. So if I had like d to the 11th, I can't divide 11 by 2. But I could rewrite this as d to the 10th times d, and I can divide 10 by 2. So I would split that up separately. And then basically that square root divides that exponent of 10 by 2, so I'm left with d to the 5, and then my square root of d. And that rule works whether it's a number or a variable. You're just looking at the exponent, and it's doing things to the exponent to make it smaller, and it allows you to bring it outside of the symbol, the radical symbol. So likewise, if I had cubed roots, so if I had something cubed, I'd want to group it in pairs of 3 or things that I can divide by 3. So if I had like the cubed root of w to the 5th, I need to group it in something that's 3 and then whatever is left over. So I would have the cubed root of w cubed times w squared, because in order for that to be 5, when you multiply, you add the exponents. 3 plus 2 is 5. So I basically took 3 of them, and then I had 2 left over. Then we have the cubed root of w cubed And then you have the cubed root of w squared, because we're trying to separate out the things that we can take the radical of, basically. That anything that I can, for a cubed root, if I can divide it by 3, I'm going to separate it out. So the cubed root and the exponent of 3 cancel because you're dividing that exponent by 3 and you're left with just w. And then you have the cubed root of w squared. So if we have something like, instead of the square root of w to the 11th, if I have the cubed root of w to the 11th, I want to group it as things I can divide by 3. And I ideally want to group it as the largest part that you can. So in this case, I would do d to the 9th. And then that gives me 2 more left over to get to 11. So you could rewrite it as cubed root of d to the 9th times d squared. So I'm going to separate out what I can divide by 3, which is the exponent of 9, from the exponent I can't divide by 3. Then taking the cubed root divides the exponent by 3. So 9 divided by 3 is 3. So I'm left with d cubed. And then I have the cubed root of d squared. So the key here is that for all of these radicals, you have to determine, is it a square root? Then I have to divide my exponent by 2. Is it a cubed root? I'm dividing the exponent by 3. Fourth root, you divide it by 4. Fifth root, you divide it by 5. Basically, that little number, if there is one, tells you what you want to group your exponents by. And you group them whether they are numbers or whether they're variables, or they can be both. You could have both numbers and letters and be able to simplify. So for example, if I had, say, the cubed root of 40x to the 7th. So we're going to have both numbers and variables. So with the number, I need to do a prime factorization because I need to figure out how I can group my numbers and things divided by 3 in groups, basically. So 40 is 4 times 10. 4 is 2 times 2. 10 is 2 times 5. So because this is a cubed root, because it's a 3, I want to group 3 things together. So I have 2 cubed, and then I have times 5. So instead of 40, I'm writing 2 cubed times 5. And then for x to the 7th, I want to rewrite it so I can divide the exponent by 3. So I can write that as x to the 6th and then another x to get me 7 total. So now in this case, if anything that has an exponent I can divide by 3, because it's a cubed root, I'm going to put in 1 cubed root here. So that's going to be 2 cubed and then x to the 6th. Anything that does not have that exponent that can divide by 3 is then put in the second cubed root. So I have the cubed root of 2 cubed x to the 6th, then the cubed root of 5x. Then you're going to take the cubed root by dividing that exponent by 3. So 3 divided by 3 is 1, so I'm just left with a single 2. 6 divided by 3 is 2, so that gives me x squared. And then I have left over a cubed root of 5x. So you have a mix of things in front and things inside. And they both have variables and numbers, but it's smaller. Whatever's on the inside is smaller than it was. So this is sort of how simplifying radicals works. You can also add and subtract radicals. If you do, you have to have a like term, and what counts as a like term is, oh, I was hoping to get a highlighter of a different color. A like term has to match inside the radical. It has to match for the actual radical. And then any variables on the outside have to match. So like terms are a lot harder to get with radicals because you have to match multiple things. Multiplying radicals is basically the opposite of what we just did, but you do want to try to simplify them as much as possible. Dividing radicals is basically sort of like what we did when you're dividing by things with different exponents. You subtract your exponents top minus bottom, or there's these things called rationalizing the denominator, and that is actually very similar to, oh, here it is, what I did with the complex numbers here, where I multiply the denominator with an opposite sign. So rationalizing the denominator when you have like square roots is you're doing the same sort of thing, but you're doing the opposite sign of the thing with the square root versus the I, but it's the same sort of process. Radicals themselves, like I could spend a whole hour just going over radicals, but we don't have a whole entire hour. So hopefully this gives you some more clarification on radicals.